Okay, so we continue our discussion of edge based or vector 2D finite element method, and what we have seen so far is the most natural way of formulating the problem unknown in terms of the total field, right. To summarize, the key thing to keep in mind here is that in order to apply the boundary condition, I had to add and subtract the incident field and apply the boundary condition only to the scattered field term. So, of the two terms that come on the right hand side, one remains which has the known information and the rest goes back. Okay. Right. So, the other way of formulating this problem is what is called the scattered field formulation. Okay. So, that is what we will look at next. So, here the variable of interest is the scattered field. Okay. So, we have already seen that H total is equal to H scattered plus H incident. Okay. What kind of a computational domain are we talking about? So, now we need to get a little bit particular. So far we just said, when we looked at, for example, the previous formulations over here, let us see the right hand side term, right. This is the right hand side term that I had. So, it is the boundary enclosing the entire domain. We did not have to ask about where is the object, where is the, I mean just the outside most boundary mattered. In the scattered field formulation, the problem changes a little bit. So, let us see what happens now. So, let us take our domain like this, okay, and this is some object. Okay. We have said that the notation we have is gamma is the outermost boundary and gamma prime is the object. Okay. So, we can call this as omega and call this as omega prime. Okay. So, domain is the union of both, total domain. Gamma is, okay, gamma is the outermost boundary, gamma dash or gamma prime is the boundary of the object, and omega, so omega is the part of the domain that does not include the object. Okay. So, for example, this object could be an aircraft and it is surrounded by air. So, air is omega, omega prime is the object. Okay. So, I mean if you want to be very particular, if I do the intersection of this is the null set. Okay. So, that makes it clear there is no intersection. I have broken up the domain into two disjoint boundaries, disjoint regions, and they share a common boundary gamma prime. Okay. So, there should be no confusion about this. Okay. So, now that I have broken up this domain into two parts, okay, let us start with omega. Okay. So, when I start with omega, I can go back to my Maxwell's equations and repeat the same steps that I did for the weak form, right. What would change? The right hand side, where I had one line integral or contour integral, I would have two. Okay. Let us again go back and refresh our memory here. Over here, when I wrote down this weak form, I got one term on the right hand side, but if I had this green case over here, then there were two integrals, right. So, that is why I had mentioned this, and this is just a simple consequence of your divergence theorem. Whatever are the boundaries enclosing the region, those many line integrals are there, because that is the outward flux, that is the principle of divergence theorem. So, those many line integrals or contour integrals are going to be there. Okay. So, what we will do, what is different now in the case of the scattered field formulation is we will write two different weak forms, one for each region. That is how we will break it up. Okay. And by the way, this total field and scattered field formulation, this is even common to other methods in electromagnetics. So, finite difference time domain, again we will visit this over here. right. So, it is actually a general principle, it is not specific to finite element methods. So, if I start with omega, what will be the left hand side will be the same as before, that is the integral over omega, right. So, what does that look like? There is a double integral over omega. First term is going to be curl of t dot 1 by epsilon r curl of h, that is the first term. Then I had a k naught squared mu r t dot h. dr, okay. This was the left hand side, and now I should write this as two different, as a subtraction of these two different things, right. The integrand has the same shape, so I won't write it two times, right. So, this is going to be t cross I am just rewriting what we had already derived. That fine? Okay. So, this is two different integrals. Is the notation clear what I mean over here? The integrand is the same for both the integrals. So, I am just writing it once, and there are two different contour integrals. Okay. Alright. Now, what is I have chosen the variable of interest to be the scattered field, right. So, I should make one clarification here. Wherever I write H, I actually mean HS, the scattered field, right. So, just to be even more explicit, this is what I mean. Testing function is the same. Which two cases? So far there is only one case. So, question is, what should be the form of the testing function? The testing function is going to be the same, because even though my variable is now the scattered field, I am going to still expand the unknown in terms of the same basis function. The basis function is going to be the same. So, testing function, whatever I did previously, is what continues to be the case. So far, there is no problem over here. Where are the issues, where are the places where we would have to take care? On these boundary terms, we have to see which one of these is to be handled carefully, okay. But that will become clear once I start with, once I go to the next region, right. So, now next is about omega prime, okay. So, I am writing two different weak forms. What happens to the left hand side? Before we go into this, physically, what does the scattered field mean? It is the field that is produced due to the object. If there were no object, there would be no scattered field, correct? So, where does it make sense? It makes sense for the observer standing out here, who can see an incident field and can compare with and without object, right? That is the physical meaning of a scattered field. If the now the object is there and the observer is inside the object, is there any sense of mentioning the scattered field? What is the physical meaning of scattered field now? Mathematically, I can define a scattered field as total minus incident, and I know incident in analytical form, let us say. Then I can mathematically define a scattered field, but inside the object there is no meaning really, there is no physical meaning of a scattered field, because what am I comparing with? If there is no object, right, I mean that case does not arise. I am inside the object is there, there is only one case. When I am outside the object, there are two cases, object, no object. So, I can compare total, incident and total. Once I am inside the object, there is no real physical meaning to make this distinction. What is scattered field, what is incident field? So, inside the object, we go back to the total field as the variable of interest, okay. So, another way of putting it is, the incident field, does it obey Maxwell's equations in free space? Yes. Does total field obey Maxwell's equations in free space? Yes. Therefore, scattered field also will obey superposition principle. That's how I was able to write down equation 1, because equation 1 has finally come from Maxwell's equations. The scattered field obeyed the Maxwell's equations because total field obeyed, incident field obeyed. However, in the case of when I am inside the object, can I say that scattered field obeys Maxwell's equations? I can't, because even the incident field does not obey Maxwell's equations inside the object. If I have a plane wave, simple case, I have a plane wave traveling through free space. Okay, so the form is e to the j omega t minus kx minus k naught x, vacuum wave number. Now I put an object inside it. Will the form of the plane wave be the same inside? We know, for example, k itself will change, the wave number inside the medium will change, the wavelength will become, it will alter, frequency remains the same, speed will change, wavelength change, we know all of that. So, we know that the incident field is not a solution to Maxwell's equations inside the medium. It won't. Okay, so let's have a look at that. So, 1D case. Okay, so what is Maxwell's equation outside the medium? d2 by dx2 E plus k naught squared E is equal to 0, right? This is vacuum. This gave me the solution of E is equal to E naught e to the minus j k naught x. Okay. Consider inside the medium. Is this guy a solution to this? What happens to the left hand side? K is different from k naught. So, this will become k naught squared plus k squared is not equal to 0. When is it equal? Only when k is equal to k naught, means no object. So, implies that incident field does not obey, incident field does not obey, but what obeys Maxwell's equations in the medium? The total field, right? That is why it makes no sense to break it up into incident and scattered inside the object. Inside the object there is one field which is the solution to this equation. Okay. Simple 1D example gives us this proof, right. So, that is why inside, so here the variable is Hs, here I am going to keep the variable as H, okay. Because always remember, this equation 1 was derived starting from Maxwell's equation. Whatever variable I choose has to satisfy Maxwell's equation. If Hs does not satisfy Maxwell's equations, I cannot arrive at this, right. So, what happens now? Left hand side will remain exactly the same, except Hs will become H. Okay. This dr that I am dr vector, just remember that this is a 2-dimensional, it can be dx dy. Okay, that is why I put a vector on top of r. What happens to the right hand side? What happens to the right hand side? How many terms are going to be there? Only one term over gamma prime, right. Okay, so now here is, it seems like I have two different sets of equations. So, the main sort of concept now is how do I tie these two things together. So, how do you think we should do it? Where will the incident, so far I do not see any sign of incident field, where does the incident field come in? At the boundary, well yeah, which boundary? There are two boundaries. Gamma dash, but I do not see it in the equation so far. So, let us deal with the equations one by one. In equation 1, I have two terms on the right hand side, right. So, what approximations or what boundary conditions need to be applied? So, equation 1 right hand side. Yeah, so we can do some algebraic manipulation of the t cross something dot n hat and yeah. So we need to apply a boundary condition on the right hand side. Question is, there are two terms on the right hand side now in equation 1, one from each boundary. So for the first term, what should I do? What can I do about the first term? What boundary condition can I apply the radiation boundary condition here for the first term? Is it a scattered field that I am talking about? First equation, is it a scattered field appearing in the variable h? Yes. Will it obey radiation boundary condition? Yes. At remember the boundary gamma is a mathematical imaginary boundary. We don't want any field to come back from it. So the natural place to apply this is gamma itself, right? So term 1 apply radiation boundary condition. Our aim is to formulate a system of equations with some of the form Ax is equal to b. I want to solve and get the fields everywhere. Boundary condition. We are doing the same thing now. We are trying to somehow get it into a Ax is equal to b, where b is known and I can solve for x, right? Except now that x vector, which is the vector of unknowns, has now been broken up into edges in gamma and edges in omega and edges in omega dash, and there is something common between the two. Okay. So term 1 I can apply RBC. Will the incident field appear inside there? Like in the total field, when I applied the radiation boundary condition on this term, I split it into 1 and 2 and incident field appeared on the right hand side. That is how this term came over here. Will that happen here? No, it won't. The incident field will not come here because it is already the scattered field. There is nothing to subtract from it. What is the need to subtract? Think physically. The boundary condition applies to the scattered field. My variable is scattered field. So all I have to do over here for this second term over here, this is what will happen, right? So it will become minus jk by epsilon r n cross hs, just like over here, right? Same logic we are applying over here. Remember what we did. This is the logic that we are applying, right? So this term is becoming this term, right? Except now h minus h incident is h scattered, which is already there, right? Okay. So this term has been dealt with. What about the second term? What should I do about the second term? Is there any particular boundary condition I can apply there? Actually, the answer is no, we will leave it as it is. So this term 2 and the RHS of equation 2 both deal with the same boundary gamma prime, correct? We are going to leave these terms as they are, okay? So, and very shortly you will see why. So the main question now that has come about is, what happened to the incident field? Where does the incident field enter inside the system of equations? Equation 1 can be written in terms of total field. That is the total field formulation. Yeah, so that's what we did previously. But in the scattered field formulation, where the variable of interest is the scattered field, now where has the incident field vanished? Or has it vanished? Where am I switching between variables? At the boundary. So if I look at one particular boundary over here, right? So over here, what can I write? So imagine two triangles over there, right? So let's take one triangle over here inside like this and one triangle over here inside, okay? For the triangle outside over here, let's call it triangle 1 and this call it triangle 2. So in triangle 1, if I look at the edge that is on, the edge of the triangle on the boundary, the variable is hs, right? So hs, and inside the triangle the variable is H. So, now the same edge has two different values. So, what is the difference between them? Incident field, right? So, if I look at it like this, triangle 2, the variable is H, triangle 1, the variable is Hs. But we know that at the boundary, the difference between the two is simply the incident field, right. So, the third equation that I get from here is going to be H minus Hs is equal to Hi. That is the third equation that I get. Okay. So, how does that translate into a system of equations? So, yeah, so if we go about it in a slightly should I say lengthier way, but easier to understand, what I would do is let us say this is my column vector x, okay, unknowns. I can break up x as edges from omega, edges from omega prime, okay. So, I can let us say that this is from omega and this is from omega prime, okay. But there are some edges that are common, correct. But what we will do is, to keep it very simple, we will do a double counting. We will count these variables 2 times, we will count these edges 2 times, and we will say that the variables are different. In one case it is scattered field, in one case it is incident field. But I will have, I can use this equation 3 to get one more set of equations only for the interface edges, and that is where the right hand side term will become non-zero. I will get an incident field from there, from this equation Hi.